Welcome everyone. Here we present our paper, MLOD, Awareness of Extrinsic Perturbation in Multi-LiDAR 3D Object Detection for Autonomous Driving. The authors, Jianhao, Peng, and Ming are from the Hong Kong University of Science and Technology. Lei Tai is from Huawei Technologies. In this paper, we focus on the LIDAR-based 3D object detection in the context of autonomous driving. LiDARs catch raw and noisy data from its surroundings. The perception algorithms, like the 3D object detection algorithm in this paper, get the location and semantic information of the object of interests for high-level decision-making tasks. Under the context of autonomous driving, the major perceptual sensors consist of LiDARs and cameras. LiDARs are more stable in outdoor environments, especially under big appearance changes. It provides more accurate spatial information than cameras. Therefore, LiDAR-based 3D object detection perform better results than camera-based methods, according to the KITI benchmark results. The limitation of LiDARs mainly comes from its data sparsity and the limited field of view. The good news is that we can use multiple LiDARs to enhance the data density and to enlarge its perceptual ranges. The multi-LiDAR systems have become standard perceptual platforms. The autonomous driving teams of Ford, Cruise, Apple, and Waymo all have adopted such settings as their perceptual platforms. With extrinsic calibration, the point clouds from each LiDAR can be merged. As a result, we can get denser measurements. However, it may inject small perturbation in its long-time usage due to the factors like vibration, temperature changes, and so on. Such perturbations might be small, but have negative effects to the whole perceptual systems. The object of interests may suffer from ghosting phenomenon in the merged point clouds. We are related to multi-sensor fusion-based perception algorithms, but we further discuss the influence of extrinsic perturbation to 3D object detection problem. To alleviate the influence from extrinsic perturbation, we first model the uncertainty caused by the measurement noise and extrinsic perturbation with uncertainty propagation methods, which is not data-dependent and has better generalization ability. We first model the extrinsic perturbation and measurement noise as Gaussian distributions. The R and T indicate the sensor extrinsics, and the P here indicates the measurement noise. They are embodied as a perturbation variable theta, which is also subject to a multivariant Gaussian distribution. And then we write down the rigid transformation and propagate the Gaussian perturbation to each 3D point. Just as shown in this figure, it is a merged point cloud and painted according to its propagated pointwise uncertainty. For more details of uncertainty propagation, please refer to the section 3 in our paper. Here is an example of propagating the extrinsic perturbation to each point. We manually set the covariance of the extrinsic perturbation variable as a constant covariance according to the sensor datasheet and real-world observations. Given a certain 3D point, we can propagate the extrinsic perturbation to each point and guess its covariance matrix. We also conduct a twin example to demonstrate the usefulness of the propagated uncertainty for geometric tasks. We consider a plane fitting task, estimating the plane coefficients from 2 frames of point clouds. The extrinsic transformation matrix of these 2 point clouds are manually perturbed around its ground truth matrix. We compare the plane fitting results with and without the help of propagated uncertainty. The results demonstrate that it performs less fitting error with the help of propagated uncertainty. The previous toy example demonstrates the usefulness of the propagated uncertainty to geometric tasks. We further extend this finding to 3D object detection problem and propose a two-stage multi-LiDAR detection network, where the stage 1 mainly fuses information from multiple LiDARs, and the stage 2 refines the proposals with awareness of the propagated uncertainty. Stage 1 generates proposals according to the point clouds from multiple LiDARs. We consider 3 commonly used fusion schemes: input fusion, feature fusion, and result fusion. They fuse the information from multiple LiDARs in the input stage, middle of the network, or the output of the RPN respectively. We tailor the RPN to support these 3 fusion schemes and to generate 3D proposals. Stage 2 refines the 3D proposals in a local region of interest. We embed the propagated uncertainty as a part of input along with the spatial information and forward it to a point-net-based parametric model. The goal is to refine the 3D proposals in terms of the low uncertainty points. As shown in this figure, the left part demonstrates a low uncertainty case. In this case, the refinement results should be similar to the proposal. The right part demonstrates a high uncertainty case. In this case, the 3D proposal is refined to cover the low uncertainty points. We conducted experiments on the LIFT dataset to answer 2 questions. Can a multi-LiDAR object detector perform better accuracy than single LiDAR methods? Can MLOD improve the robustness of a multi-LiDAR object detector under extrinsic perturbation? We compare 4 settings. Single LiDAR cases. The LiDAR top, LiDAR left, and LiDAR right represent 3 single LiDAR-based 3D object detection methods. One-stage multi-LiDAR fusion cases with input fusion, feature fusion, and result fusion schemes. Two-stage multi-LiDAR fusion cases, where we consider the propagated uncertainty in the 2-stage framework, and 2-stage multi-LiDAR fusion cases with the online calibration modules. The experiment results first demonstrate that the multi-LiDAR system improves the accuracy compared to the single LiDAR cases, and the 2-stage methods perform better or comparable results than their 1-stage counterparts. We also compare the robustness under different level of extrinsic perturbation. The level of extrinsic perturbation is parameterized with alpha, and the bigger alpha determines the greater extrinsic perturbation. The experiment results demonstrate that the 2-stage MLOD fusion methods perform better results than their 1-stage counterparts. The same results also hold if considering the online calibration modules. In the following slides, we will demonstrate some qualitative results. This figure demonstrates the scene perturbed with the alpha equals to 0.04. We can see massive noisy points, and about 50 cm misplacement appears at about 35 meters away, which is indicated by the red arrows. MLOD performs better results according to this zoom-in view. Here, we demonstrate a sequence of qualitative results under low level of extrinsic perturbation. In this sequence, we can observe small misplacement exist in the merged point clouds. The 1-stage counterparts have more false detections due to the ghosting influences. Here is a sequence under high level of perturbation, where we set the alpha equals to 0.1. We can see a lot of noisy points here, but MLOD can also perform relatively better results than the 1-stage counterparts. In this paper, we quantitatively analyze the effect of extrinsic perturbation in multi-LiDAR detectors and demonstrate a simple plane fitting task with the uncertainty prior. we propose a two-stage network for multi-LiDAR object detection and conduct exhaustive evaluation on a real-world self-driving dataset. In the future, a promising direction is to extend this work to other combinations of sensors like LiDAR camera radar platforms. That's all for this video. You can refer to the website for more information and details. If there is any questions, please feel free to ask. Thank you for watching.